Greetings and welcome back to a new video about Extra Element Theorem. We will apply this theorem in this case to a pure resistive circuit where we have 5 resistors in the Wheatstone bridge configuration. And the Wheatstone bridge configuration is most often encountered in sensor applications, so it is very handy to also see this in this form. So let's see how we can use this Extra Element Theorem. Use the Extra Element Theorem, EET for short, to determine the input resistance Rin between the nodes A and B. In this case, we see here R1, R2 up to R5. We also have here the input current source, In, and the associated voltage across these two nodes, so which is the Vin. So the ratio using Ohm's law, Vin over In, will be then Rin. So we will designate here, that's actually our first job, first step is designate your extra element in this circuit. It can be anything, it can be R1, can be R2, doesn't matter. I have chosen here this R5 and you will see why I do that, because that's the most convenient selection of the extra element to ease in your calculations in this example. You can also go for R1 for example, or R2 or R3, it doesn't matter, that will be a little bit more complicated, but the end result will be exactly the same. So I will go for R5 and then your formula will be then Rin, your input resistance Rin at that condition where the R5 is open, and then times a factor which is the 1 plus the nulling resistance divided by the R5 itself, and then again over 1 plus the driving point resistance Rd over again the same R5. Of course we will calculate this step by step here and we will work out the actual value using also numerical values for these resistors. Okay, first let's see what the first step is. We will remove our R5 here from the circuit and calculate the input resistance associated with that one. That means actually this part. So actually the current source and the associated voltage source is gone. You only look between the nodes A and B and you also remove the R5 and then you determine the resistance here. So it's actually this part. So how to do that? Well, if you look at this, since this is open, R5 is gone, the R1 and R3 are actually in series, so they create one branch. And R2 and R4 is also creating a series resistor, and that's also another branch. So these two branches are actually in parallel. That means R1 plus R3 is in parallel with R2 and 4, So that's the first step. Okay, the second step is we will disable now the input current source. In this case, that means we will make it open. That means disabling your current source. And we will determine now the driving point resistance, Rd, again looking between the nodes of the resistor R5 we have chosen as our extra element. Now the circuit will be like that. So we have here an open circuit since the current source is now open. That means disabled. And we will look again between the two nodes of our R5. That's actually here. Now, since this is open, that means you can actually forget about these connections here. So what you see is between these two nodes, you actually see that the R1 and R2 are now in series together, and also R3 and R4. And they are again in parallel. So the total combination, that means Rd, is the parallel combination of the series combination of the R1 and R2 and R3 and R4. That's actually shown here. So that's the second step. Okay, the third step is null the input voltage source, which is now actually this. So we make actually this short. It's not necessarily grounding. And then determine the nulling resistance, which is then called R sub n, between the nodes of the resistor again R5. So now the circuit becomes like that. So it's almost the same, only this part is now shorted. That means the Vin is 0. Again, you look between the two nodes where we have our extra element, R5, and that's now this Rn. So what we see, well, in this case, we have the A and the B nodes. They are actually at the same potential because this is practically short. And now we have here the R1 and the R3 here. They're actually in parallel, which is the same for R2 and R4. And now you see actually the parallel combination of R1 and R3 in series with the parallel combination of R2 and R4. So that's actually what we see here as R sub n. So we have now actually 3 elements for our formula. This was for the first step, the Rd from the second step and Rn from the third step. Now we can apply, which is the final step, step 4, this formula and then calculate the Rn. And this is now the expression in the formula form. And now we will use the actual values and also verify that shortly using the simulations. Okay, this is now the expression we have found. And we will now use these values for R1 up to R5. And these are the values. And we will calculate here the actual Rn and verify that using the simulator. We start first with this part. What I do is I will first calculate the series combination, so R1 plus R3. We're looking at actually this one, so 10 plus 60, which is 70 ohms. And then R2 plus R4, 20 plus 40, which is then 60 ohms. And now the parallel combination of these two parts, which is actually then, again, the formula, what we know from the parallel resistors, two resistors. So 70 times 60 over the summation of these two. And you get exactly this value. I will use the exact value because I really need that, otherwise I will get some rounding up errors in the final answer. So 420 over 13 ohms. Okay, that's the blue part. Now I will now continue with this green part. Now again I will use the series combination of the resistors R1 and R2. It's 10 plus 20 is 30. And then R3 plus R4. That's actually the next one. So 60 plus 40 is 100. And then again the same calculation as we have done it here. So I will now use the parallel combination resistor formula and I get here 300 over 13 ohms. So you can do that actually in your calculator. So that's the part here in green. Now the part here in pink, that's actually the parallel combination of R1 and R3. That's actually here. So we get here again exactly 60 over 7 ohms. And for R2 and R3, the similar calculation, similar formula, and now you get here 40 over 3 ohms exactly. Now if you now add them up, because that's need to be done, because now we have to add these two answers, and then you get here 460 over 21 ohms. All right, now we're almost done because now we know the elements here, so we can now substitute that. Then we get the following. So 420 over 13, that's actually from this blue part, times 1 plus, now you get this actually this pink part, which is then 460 over 21, over 100. Why? Because that was our R5, which is our extra element. That is what we have chosen. And then divided by 1 plus 300 over 13, that's actually from here, green part, divided by again the R5, looking at the formula. Okay, that's actually this. Now you can just punch this in your calculator and you get this result, which is the 32 ohms exactly. So we will now also verify this in the simulator. Okay, let's do that. Now this is now the circuit in the SPICE simulator. I use the Tina TI SPICE from Texas Instruments. You see here again the R1, R2 up to R5. In this format I have actually drawn that in sort of an H circuit. So you see the resistor here, which is then measured by this ohm meter, and you see here Rn is exactly 32 ohms as we have calculated. So this is actually nice and verified here in this simulator. Well, what happens if you choose another element, another extra element? You can try that. You can try to choose, for example, R1. You will get exactly 32, but the calculation will be a little bit more work, or maybe also a little bit complicated, because you cannot recognize maybe the parallel combinations or the series combinations easily. So in this case, and you get actually this practice and experience by working out more of these examples. And I've chosen this R5. Why? Because I saw that if you choose R5 as your extra element, you get really nice formats in the steps using the extra element theorem. Alright, it was our example considering the extra element theorem, specifically used on a pure resistive circuit, in this case the Wheatstone bridge, and we have applied that and calculated our equivalent or input resistance. If you have any questions, comments, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.